Hello everybody. Hope you guys are all doing well. I'm Adwin Ross. I'm an iOS engineer, and I'm currently working at a company called Measure. I've been an iOS engineer for about 11 years now. I've worked a bit on React Native as well, but primarily on the Objective-C and Swift side of things. So when I started out my career, iPhone 4S was just about the latest and greatest technology that Apple had to offer. That should tell you how primitive I am. So in both personal as well as professional capacity, I've worked on more than 50 plus iOS applications. And over the past year or so, I've been working at Measure, and we are working really hard on creating a monitoring SDK for multiple different mobile platforms. So over our experience, what we have realized is that even though there's quite a few monitoring tools out there, none of them seem to be mobile app first. Now, you look at most of the platforms out there, they either an extension of an existing web front-end system, or they are a sort of a wrapper on top of a backend system, backend monitoring tool. And we feel that that shouldn't be the case. We should look at mobile app monitoring as a first-class citizen rather than just an extension of an existing monitoring system. So that's how we got the idea of building our own monitoring SDK. Now, even though I've worked on creating and maintaining a few SDKs before in my career, I think creating a monitoring SDK was uniquely challenging. And I'm here to talk to you guys about what sort of challenges I faced, how I worked on creating SDK that essentially measures, but it does not meddle into the host app's performance. Right. So we all know that creating and maintaining any sort of SDK is a huge hassle within itself, right? So you need to make sure that you support multiple platforms like iOS, Android, React Native, Flutter. Then within these platforms, there's a whole bunch of distribution complexity that you have to deal with. Look at iOS itself. You have to make sure that you distribute via Swift Package Manager or Cocoa Pods, or ship it off as a standalone library. You need to make sure that you give the developers the ability to link your framework statically or dynamically. Again, once you're managing all of these sort of complexities, you need to make sure that your code is also written in a way, because all of these distributions channels save resources differently, deal with paths differently. So that increases your code complexity as well. Again, just because you're building a SDK, that does not mean that you're going to create everything from scratch. You are inevitably going to end up using some sort of dependencies in your SDK as well. And dependency management can become really tricky when your host application is also depending on the same sort of dependencies that your SDK is as well. With every new release of new APIs or new features in your SDK, you need to make sure that you don't break everything that you've created before, making backward compatibility something that is very critical. Again, documentation and testing are something that you need to do for any single iOS application that you create. But again, with third-party tools, what ends up happening is that you never really know what sort of an environment you will be running in. So testing becomes really critical. And documentation at the end of the day should be clear and robust enough that anybody who is looking at your documentation should be able to sort of integrate your SDK pretty easily. Now, even though these are some complexities that any SDK creator might fail, creating a monitoring SDK sort of adds another layer of challenge to the existing set of challenges. So one biggest difference between any normal SDK and a monitoring SDK is that a monitoring SDK will always run throughout the life cycle of your application. Take an example of Stripe. If you're integrating Stripe to your project, you integrate Stripe, maybe you make a couple of payments throughout the life cycle, and you just take the control back from the SDK. And Stripe does not essentially, even if something messes up in Stripe, it does not cause a huge amount of issue in your application. Whereas because you are continuously running in the background as a monitoring tool, looking and collecting performance related data, any overhead that you add on top of the existing host app, it becomes a really huge challenge. So you need to make sure that you write very performance efficient code. At the same time, you cannot really be the source of the problem yourself. You need to make sure that any code that you're shipping, even if it messes up or it ends up failing, you need to fail very gracefully, and you should never crash the host application. Given that you're collecting a huge volume of data every single time, again, everything from CPU related data, memory related data, lifecycle application lifecycle events, view controller lifecycle events, you just end up collecting so much data that data management and data export becomes a really tricky problem to solve. So think about somebody using a user using your application in a very remote location where the network isn't all that stable. Now, you need to make sure that you collect enough information and you have a decent enough cache eviction policy that, if there's no network condition, you don't hold up too much space in the user's device. At the same time, you sort of need to make sure that you just don't keep deleting every single data point that you collect. You need to, export out some data so that developers also have a understanding of how the users are interacting with your app. So striking that perfect balance is always very tricky. And again, on top of it all, it's not just about collecting every single piece of information available. It's also about knowing what not to collect. iOS has a very strong policy around privacy, and we need to adhere to that. Along with that, there can always be, some sort of local government or region-specific compliances that you might need to adhere to as well. So now that we've talked about how challenging creating a monitoring tool can be, I'll just go through a few issues that I personally faced and how we ended up solving those problems. So we all know that any monitoring tool is incomplete without a crash reporter. Now, I'll explain to you guys briefly how a crash reporter works, but we don't currently use our own implementation of a crash reporter. Across the industry, there's two open source libraries available. One is called KS Crash, other one is called PL Crash Reporter, and every tool across the industry relies on these two crash reporters because operating in a crashed process and generating a bunch of data around it can be really tricky. At Measure, we use PL Crash Reporter under the hood to collect and capture crashes and report it back to the developers. So firstly, let's start by talking about what a crash really is. So a crash is essentially nothing but a sudden termination of your app because it tried to do something that it wasn't supposed to. Now, any crash that could happen would roughly fall into these four categories. So CPU related crash can happen when you're trying to do something that the CPU itself wasn't able to execute. You can think of like certain numeric operations. You're trying to divide a number by 0, or you're trying to multiply a number by nan, not a number. In those cases, the CPU itself isn't able to execute the instruction, and it leads to a crash. Secondly, of course, if you don't adhere to iOS policy, there are certain cases where iOS itself decides that it needs more resources and it could go ahead and crash your application. If your app is within a deadlock and it's not responding for more than 20 seconds, iOS goes and then it crashes your application. Your app runs out of memory, iOS can go ahead and crash the application as well. Now, these first two conditions are generally very rare, but these sort of issues can, of course, happen. The last two programming language related issues and developer triggered crashes are the crashes that most people end up facing. So programming language related crashes would be anything from you trying to access Objective-C or Swift APIs and the runtimes in a way that you're not supposed to. So think of array getting out of bounds, you trying to force unwrap an optional you not having handled a exception that you were supposed to handle. At the same time, developers themselves can add a bunch of preconditions, asserts to their code to make sure that anybody who is using a particular piece of code is doing so in an accurate and reliable way. Now that we know that what a crash really is, let's talk about how actually OS goes ahead and crashes your process for you. So the way it essentially does is that it does it via signals. So signals are nothing but low-level predefined notifications. So if you ever had to hit Control C on your terminal app to kill a particular process that was running in the terminal, what you end up inevitably doing is, as soon as you press Control C, you send a signal to the shell. That signal is called signal interrupt, SIGINT. You guys must have seen it somewhere in the crash reports. And then as soon as that SIGINT is sent to the shell, it knows that it needs to terminate the current process that is running. And then it passes on that interruption signal to the kernel, and then kernel goes and stops that process. Crashing an app works in the exact same way, just in reverse. So whenever OS decides or the kernel decides that you're trying to do something that's not allowed to, it will pass along a signal to the host application, and the host application will handle that signal and crash gracefully. Now, here are a bunch of signals that you must have seen in any crash report that you've seen. So first one is what's called a segmentation signal. So this usually gets thrown around when you're trying to access any invalid memory address. So think about if you're trying to access a memory location that has already been freed, or you're trying to access a memory location outside the scope of your memory layout of your application. Sig abort is a sort of signal that's thrown when you call asserts, preconditions, and fatal errors from your code. So this is something that most commonly people end up interacting with. And the last one is pretty self-explanatory. Sig kill, essentially, it's the kill signal. If a sig kill is thrown, sig kill is usually thrown by the operating system when your app is in deadlock, or if you get through any sort of a watchdog termination, then the OS will send a sig kill signal towards your app. Okay, now that we know that it's signal OS uses signals to essentially terminate our process, we now understand that if we have a way to sort of intercept the signal when it's being delivered to the application, we can more or less presume that the app is about to get crashed. So that exactly is the job of a signal handler. Signal handler is nothing but a function that essentially looks up for these bunch of different signals that are being thrown around. As soon as a signal handler receives a signal, the signal first is thrown by the OS to the process. The process is just about to kill itself, and before the process is terminated, the signal handler is run inside the same crashed process itself. Now, because it's running inside the same crashed process, you don't really have access to Objective-C runtime and Swift runtime APIs. You can't even use something as trivial as nslog or print statements, because the idea being it can lead to some sort of a data corruption, or it can lead to some sort of a deadlock. Assume that your Objective-C runtime, when the code crashed, your Objective-C runtime was holding on to a lock, and you use another Objective-C API at the same time. Now, both the APIs are sort of, because the process itself has crashed, the lock will never be released, and the second process will just end up waiting for the lock to be released, resulting in a deadlock. So that's why you can't really access any of those Objective-C Swift APIs that you're familiar with. Just about the only APIs you are allowed to use are 30 or 35 low-level system APIs, of which write, open, and close are some of them. So what ends up happening is, when you're using any sort of a crash reporting tool, right, as I mentioned, KS Crash or PL Crash Reporter, they implement their own custom signal handlers. And as soon as the crash happens, they will handle the signal. They will generate the current backtrace. They will generate the current register informations. and at the same time they will capture some sort of a metadata of the current device that the crash happened on. They will save everything into a crash file and save it in the local file system. So this is how a PL crash reporter uses these low-level APIs to, essentially generate and save crash logs. Now, we had this one particular requirement where we not only wanted to collect the crashes, but we also wanted to add some metadata along the crashes as well. So, as I mentioned, we don't have access to Swift API. So what we ended up doing is that we ran through what all APIs were available to us on the system level, and we found out that we had the open and write APIs available. So open and write are nothing but system level APIs that allow you to open a particular file and write into a particular file. So what we do is, as soon as our SDK is initialized, we call the prepare crash file function. What it does is it opens up a file with the predefined crash file path, where we essentially use the file system itself, and we create a simple path in our local cache to create this file path. Then we essentially tell it that we pass along these options which essentially tell the open API as to how this particular file would be interacted with. So OWR only means write only access. O create means if the file does not exist, create it. O append means if the file is already available and there's some data inside of it, don't override it, just append to the existing data. And these last ones are essentially read and write permissions set for the owner, meaning that only the current process, which is the owner of this file, has the read and write permissions for this file. If this API succeeds, we get a file descriptor, which is nothing but, think of it like a pointer to the local file. So you don't get a file path in return, you get this particular file descriptor. And we need this file descriptor at the time when the crash happens, because file paths are not safe to be called in crashed process, but a crashed file descriptor is a crash safe API. So as soon as the crash happens, what inevitably ends up happening is that we have our own signal handler as well. And then that signal handler calls this write crash data function. Firstly, we go ahead and check whether the file descriptor is a non-negative value, meaning whether the file was opened successfully or not. If the file was opened successfully, we already have pre-written JSON data in a string format. So we convert that string into a C string, which is nothing but a binary data dump using UTF-8 encoding. And then we use the write API to essentially write all of these data into the particular file that we have just opened when we launched our SDK. So this is how we use the crash reporter, its powers, and low-level system APIs to add some sort of a metadata to our crashes. So now that we have talked about crashes, let's talk about something more fun and interesting. So we had this one, another particular requirement that we understood that, yes, sure, logs and just raw binary data can help developers out. But at the same time, it would be a way better debugging experience if developers got to actually see what the users themselves were seeing. So we tried to go ahead with screenshots, but I'll explain it to you guys in later slides why that was a bad idea. And then we ended up creating something called something what we like to call a layout snapshot. I'll just show you guys an example for the same. So this is nothing but a normal collection view, got a bunch of vertical list items, got a bunch of horizontal items. Now, how do you sort of represent this, visually to a developer, at the same time making sure that the privacy of the user is not compromised? So this is what we came up with. This is what, on the right side, this is what we like to call a layout snapshot. So it's nothing but the current snapshot of the current view hierarchy that is being displayed on the screen of the user. So as you can see here, it's what we essentially go ahead and do is we traverse through the view hierarchy, collect all the different views that are available, and we generate the frames for it, and we just pass along those frames into a SVG generator, which then just goes ahead and generates this SVG for us. Of course, everybody must be thinking here, why not go ahead with screenshots? So we did think about screenshots first. One of the few problems that we have with screenshots is that screenshots are generally very heavy because they are a PNG representation of the current UI. Even if you end up compressing them, you end up with screenshots that are hundreds or 200 KB sizes. At the same time, we have tested this out internally. Layout snapshots are just SVGs, so even the most complex of UIs can be represented in less than 5 or 6 kilobytes of space. Again, as I mentioned, layout snapshots are way more privacy focused than screenshots. Whenever you take a screenshot, you have the additional hassle of making sure that you redact any information that is there. So layout snapshot sort of takes all of that out of the equation. Uh, Layout snapshots at the same time are way more efficient as well in terms of memory and CPU usage consumption. So what we found out that the P95 times for even the most complex of layout snapshots did not take more than 15 milliseconds, whereas the P95s for screenshots was around 80 milliseconds. Even when you take a look at the average times, layout snapshots was around 4 or 5 milliseconds, whereas screenshots would generally hover at around 70 milliseconds. And that 70-80 milliseconds is just the cost of actually taking the screenshot. Then you need to do some sort of a post processing on top of it as well, where you essentially go ahead, redact all the information, add a masking layer on top of whatever views you want to hide out, and then essentially go ahead, save it to the local file system. And all of that process becomes heavy. So because we are able to sort of generate these layout snapshots that are so lightweight and so efficient, we then essentially got this superpower that we could essentially attach layout snapshots for every single gesture that was provided that was provided by the user, without actually having a lot of trade-off in terms of efficiency and space. So that's what we went ahead and did. So let's look at some code now. The thing with layout snapshots is that all we do is we look into the current view hierarchy, loop through it, and then essentially collect all of these frames and then pass it along to the SVG generator. Now, the one gotcha there is that every single time a view is created, its origin is always in relation to its immediate parent view. It's not in relation to the root view. So what we do here is we use the view.convert API to convert it into the relation with the root view. Now, second line here, as I mentioned earlier, we wanted to collect layout snapshots every single time the user interacted with the app. So we just check whether the current view is the target view or not, meaning whether both of them are pointing to the same memory location. If so, go ahead. The current view is the target view. And then we recursively go through everything and collect the frames for all the subviews inside the current view. And even though this recursion looks like it's going to be pretty heavy, we have tried it out with a view depth of even 30, 40, and even something as absurd as 1,000. It actually does not take a lot of time. So last sort of thing I wanted to discuss with you guys was our sort of struggle around trying to collect CPU usage information. Now, as trivial as it might sound, CPU usage information collection ended up being one of the trickiest things we had to solve. So iOS does not provide you a direct API where you can just get the CPU usage information and move ahead from there. What iOS does do is that it has a host statistics API. Now, what ends up happening is that every single time the iOS chip performs a operation or runs an instruction, what it will do is it will maintain these three different counters. One is called user, system, and idle. Every single instruction it runs, it keeps on updating these three different counters. So what you could do is you could use this whole host statistics API, pass this host CPU load information flag to it, and then it will give you back this CPU counter information. Now, what you could theoretically do there is that you could, pass along 2 points. You can take two timestamps, have get the CPU counter information for both timestamps, get a difference from them, and essentially have a rough estimation of how much work was done by the CPU in between those two timestamps. Now, the problem here is that even though you get user and system level information, the problem with user level information is that it's not particularly process specific. So if, let's say, you have your app running in the foreground and you've got some other app in the background with its background tasks enabled, and it is downloading a huge file from somewhere in the network. Now, what ends up happening is that that CPU usage also gets added to the user, even if your app is not really consuming that CPU usage. So even though this is very simple and lightweight to use, it does not reliably give you how much CPU usage was consumed by your particular process itself. So we went ahead, we scratched through some old Darwin APIs, and then we figured out that even though we don't get process level CPU usage information, you can get very accurate thread level CPU usage information. So that thread level CPU usage information is provided by the thread info API. So what we do is essentially we generate a list of all the threads that are being used by the current process, and we pass it along, and we get that information using the task threads API. Again, this is a very low level Mac API. Then once we have all of that information, we essentially loop through it, and then we call thread info for each of these individual threads. As soon as we get that particular thread information, that object will contain the CPU usage, and the cumulative CPU usage of all these different threads is the CPU usage of your particular process. It's the exact same mechanism that Xcode also uses to show you the CPU usage. And we have implemented the same thing. So there's essentially no discrepancy between the data. Now we have, again, we have run a bunch of tests here, and we have figured out that the P95 time for this process, even though it might sound complicated, is around 900 microseconds, which is not really much. So given that it takes such less amount of time, it enables us to collect this information every 3 or 4 seconds, and thereby giving you a beautiful graph of how what the CPU performance was for your particular application. Let's check out some code. I know this looks horrible, but let me take you guys through it. So firstly, as I mentioned, we use the task threads API. This API essentially gives the current, gives us the list of all the threads that are currently being used by the process. So that information is saved into the thread list and thread count, pointers, which you can see as are the parameters for this function. Now, what we do next is essentially, so when you get this list of thread IDs, right, it is nothing but the thread IDs in an array. So then we go ahead, loop through these thread IDs, and then we use the thread info API to essentially pass along the thread ID. And then we pass along what type of information we want. So the CPU usage information is in the thread basic info API flavor. So we pass along that particular flavor, and then we pass along the thread info object where we actually want to save the save the thread info object. Now, what ends up happening is that there's this thread info that you see here. It's not really object; it is an array. So they use arrays locally to make sure that this API is really fast. So what we do is we convert it into another basic C structure called the thread basic info. And the indices for this thread info array are always predefined. So the index 7 will always contain the flags, and the index 4 will always contain the CPU usage. Now, all we do is we just check if the current thread is idle or not. If the current thread is not idle, we just turn the CPU usage into a percentage value. and add it to the cumulative CPU usage. So that and using this process, we are able to essentially get the total CPU usage for a particular process. Again, as I mentioned, because this is a low-level C API, the onus of freeing all the allocated memory falls on you. So anytime we differ from this function, we just deallocate all the memory that we have used. So it's not just that we collect CPU usage information and crashes and layout snapshots. We can collect a whole bunch of different information. So we collect everything from launch events to gestures to lifecycle events and HTTP events as well in an automated manner. On top of it all, you have a bunch of other custom events that you can add as well, along with traces and spans. Now, again, as I said, current tools across the industry are not particularly streamlined for mobile developer usage, and we wanted to change that. And we understand that debugging can really be tricky. Sometimes the bug is just right in front of you, and you can't really have an understanding of what's going on. So we designed this new whole new feature altogether called session timeline, and I would like to give you guys a brief demo for the same. So as you can see here, what whenever we want to test our SDK, we integrated it into the Wikipedia app, which is also open source. So this session that you see here is a proper session from a Wikipedia iOS app where Measure was integrated. Now, again, for any session that starts, you have the basic information of the session itself. This user ID is any custom user ID that you might have added, the duration, what device it was on, what was the network type. And again, as you can see here, yeah. So as you can see here, you have this proper, graph and timeline where you can just see the total memory usage across the timeline for a particular application. And again, below you have a bunch of different events that were collected in an automated manner. So you can just keep on scrolling. And once you keep on scrolling, you see that the timeline above scrolls along with the events that are being scrolled. So you can just go ahead, keep on scrolling, and essentially figure out and understand how the user actually interacted with the app. Now, let's take a look at a few gestures that the user might have performed. So I'll just, yeah. So take a look at this click gesture, right? So every single time the user interacts with the app, performs a click or a scroll gesture, we take a layout snapshot, as I mentioned to you guys earlier. So here, as you can see the layout snapshot very clearly. And you can also see that, this particular yellow box, which was the view that was clicked, getting highlighted. So it's not just that you get to understand what particular button was clicked. You don't particularly need to go through the code to understand it. You can just visually have a look at it. Another better example would be something like a tab bar. As you can see here, a UI tab bar button was tapped on. And even though maybe some of you might not have used the Wikipedia app, but you can clearly see that there is a tab bar here, and the second element of the tab bar was tabbed. So you don't need to go too far to understand what was going on, and that is the power of layout snapshots. Again, let's say we all front-end developers been in a situation where our app is behaving perfectly fine, but it's the HTTP requests that are failing. So we try all of those well in an automated manner. And again, you can go ahead and see whether a particular response was correct or not. What was the duration that that particular HTTP request took to give you the data. Again, all of these are opt-in features. You can, of course, go ahead and disable all these features if you want to, if you have any sort of privacy concerns. Now, where this sort of a particular timeline-like feature helps you out is when you want to understand some sort of a discrepancy in the user behavior. So let's take a look at this, right? I can very clearly see here that there's this one CPU spike happening here. Now, let's say I just want to understand what's going on. What I can do here is I can just use this particular seek bar and just point point the seek bar to a point where some place before the CPU spike must have happened. So as soon as you do that, the event list moves along with it as well. Now, as soon as I do that, I see here that, okay, one particular button was clicked, and I can see here in the layout snapshot which button was clicked. Then a few events got triggered. You can just go scroll through it. Let's move ahead a bit more as well. Now, second thing again, I see that I'm in the middle of my memory usage spike, CPU usage spike, and I see that another particular button was clicked here as well. And now, because I know that the CPU usage has spiked here, that whatever issue that there is that has led to this particular spike has happened between these two particular user interactions. If you go here and take a look at all the different types of events, you can see that there's a huge bunch of view controllers that are being initialized here. So you've got a welcome container view controller, animation background, animation foreground, welcome panel, welcome analytics. So now my best guess is that the Wikipedia app CPU spike is happening because of that. But again, because you have such a consolidated view and the data is presented to you guys in such a beautiful manner that you can debug this pretty easily and sort of help you figure out what the root cause of a problem might be. So this is what we've been working on at Measure for past year or so. Hopefully you guys enjoyed the demo and found it useful. If you guys want to check us out, you can have a look at us at repo.measure.sh. We are completely open source. Please go ahead, check the iOS side of things, integrate it to your apps, and any feedback or contribution is appreciated. Thank you very much, guys. You guys have been a great audience. Thank you.
Yeah. Can you hear me from there?
Sorry?
Can you hear me? that's
yes.
Over there? Yeah. Okay.
Sorry?
Yeah, okay. I will go closer.
Yeah. I think the demo was great. I just have a question about KS Crash Reporter. Have you evaluated that?
Just one thing. Can I just close the recording, Florian?
Yeah, sure.
Yeah.
Except
okay.
if you want to show us more stuff later, you can start.
Yeah. Yes, Prashant.
Yeah. So I was just asking if you evaluated KS Crash Reporter also.
Yeah, we did evaluate KS Crash Reporter. Now, what ended up happening with the KS Crash Reporter is that the way it was generating the backtrace, it was relying on a lot of Objective-C APIs to do so. And the biggest culprit was just one single line of code, which was essentially them trying to get the current process name and the thread name. Now, what ended up happening was they were using Objective-C APIs to do so. Now, even though that we don't currently get the thread names, but we do get the thread IDs using PL crash reporters. So there were a bunch of crash reports that were actually getting missed in KS crash report altogether because it was resulting in a crash of its own and it was not able to track the crash itself. So in our internal testings, we found out that PL crash reporter was just slightly more reliable. And that's why we decided to go ahead with it. Another reason being that PL Crash Reporter is maintained by Microsoft. So there's a very strong open source community around it.
Yeah, I think the reason I asked this is that we also have our in-house Crash Reporter. And we also use PL Crash Reporter, but the problem is PL takes like there is a little overhead in the start time when it is in progress. So we were looking to see if we can reduce the start time, and so that's why we were developing case, but
so again, so KS Crash Report again has that one advantage where you can export out the report using a network call at the same time when the crash is happening. But again, the problem with that is that it's not particularly reliable. And again, a crash can happen when that whole process is happening. And we wanted to make sure that any monitoring tool, the key thing is that you at least report the crashes properly. And that is like the base of it. So we wanted to make sure that we do that properly.
Maybe one more question. And
yes.
Maybe I'll go to others.
Yeah.
So, go ahead. So, because in Gojek, for example, we spend a lot of time with Instabug,
Yeah.
and maybe we always use Firebase as or Crashlytic as kind of the gold standard, right?
Yeah.
So we can do some testing, like, okay, let's generate crashes with this, and then compare it. Like,
Yeah, so we did do that, and again, so what ended up happening is that the demo I showed it to you guys at the end, right? There were so many things that people liked about it. So one is, of course, if there is any crash attached to a session, that gets shown in the timeline itself, so people can go ahead and see very visually as to what's going on. On top of it all, a lot of people just preemptively ended up figuring out bugs. So iOS, there's one big thing that you need to do is that you need to figure out if there's any memory leaks or not. And that can be really tricky. And we are also working on certain methods of actually figuring out in runtime itself how we can, check for memory leaks. But one thing that one of our users is doing is that they continuously just keep looking at the memory usage data. And the point when it starts spiking, they just look at the backtrace for the past minute or so before the user actually encountered the leak or the crash. And because of that, they at least have a rough estimation of which part of their code base is screwing up. So even having that estimation helps developers a lot, is what we have seen. Again, regarding Firebase and all these other tools, right, as I mentioned, they have never really been mobile first. Firebase has always been like a analytics tool that ended up being a performance monitoring tool. Sentry, I think, is doing a good job, but again, it's a web front end focused tool first, and its biggest selling point is that it's a consolidated ecosystem where you can track the whole. You can find a very good high level overview, but you never really get the granular data of debugging and figuring out what the user was doing. Yeah,
they just acquired Immerse. So that's something they want to change their image now.
Yeah.
Any other questions there?
Yeah.
Yeah.
So we use Sentry and Emerge.
Oh.
And we're trying to use the session replays now from Sentry.
Yeah.
Which, seems to work well. But it is a screen recording.
Yeah.
Just redacts all your text.
Hmm.
And that one works, right? But I'm wondering, how would your layout work in a pure Swift UI app?
So given that Swift UI internally still ends up using UIKit components to render, we have tested it out with Swift UI components as well. Where Swift UI requires another set of integration is calculating lifecycle events. So right now we can just generate TTID spans for each view controller because we know the lifecycle of a view controller, whereas you don't particularly have that information when you're dealing with Swift UI views. So we have created wrapper views, which you can wrap your existing Swift UI view around if you want lifecycle related information. But if you just want a layout snapshot of it, that works absolutely fine with Swift. Our current layout snapshot implementation works absolutely fine with Swift UI as well.
And all the gestures and everything still works.
Yes, everything works fine. So we found this while we were actually creating all of these features. That's when we found that even though Swift UI is, it's more of a paradigm shift than a whole UI rendering shift. Yes, you can still have that whole Swifty reactive thing on top of it. The way it actually ends up rendering things is on the UIKit layer itself. It just removes that UIKit management system out of your hands into this beautiful Swift UI way of designing things, but internally ends up just using the whole UIKit system.
Yeah. What's the size of your package compared to Sentry, for example?
Yeah, so what we have seen with our clients is that they see about half of megabyte increase in the final IPA. Somewhere between 500 kbs to 600 kbs, but not more. I think Sentry's is about 1.5 2 megabytes, right? Yeah, yeah. So we managed to do that. So if you look at our code base, it's all completely Swift. We wanted to make sure that we use as little as older Objective-C and C APIs as possible. Even if we end up making use of these older C APIs, we try and do it in as swifty way as possible, because we can very clearly see that that is the future that Apple is also pushing towards, and there will come a point where we have to go ahead and migrate all of this old code base. So given that we just started a year back, we just decided to stick to Swift and focus more on the Swift UI side of things, and a bit more on the UI kit side of things as well.
And you said it's open source, so does that mean that we can self-host?
Yeah,
yeah. Actually, self-hosting is a good way.
Yeah. So currently we support iOS, Android, as well as Flutter. React Native is on the way. I'm currently working on the same.
Check this out.
Any question? Other question?
Will you guys support AppKit for the desktop apps? Like,
so I think we have tested it out with the desktop apps. It does work, but it's not primarily designed for it. The primary support is currently for iOS and iPadOS. All of the features work, but certain features like layout snapshots do break when you're dealing with Macs. The problem with the Macs is that the resolution is never clear, and it's just the range of devices that you have to support with Intel and M series MacBooks being a thing. It just becomes really difficult to sort of get a few set of information that we want to. Once we sort of nail this whole mobile experience, we will move on to supporting Mac OS as well. Currently, there is still Mac OS support, but certain features will be unreliable.
Yeah, I have one more then.
Yeah.
For the layout snapshot, can you set like different, let's say, tints to specific elements? So when you render the layout snapshot, the tab bar would always be green, the rows would always be specific color. So when you look at the snapshot, you immediately can just see what it is. Is that possible?
So it is not possible, but again, we can do it.
It's not implemented yet, but
yeah.
it could.
Yeah, exactly. If you want that sort of feature, we can do it on both SDK side as well as the dashboard size. Anyways, you guys have that information that this is particular this. So you will always have that class information, whether it's a button that's been tapped or a text view that has been clicked. So you will always have that information. We can figure out how to implement it, but sure, this is doable.
If I set IDs or tags on a Swift UI view, will that automatically propagate over?
Yes, we get in the accessibility identifier information directly. Yeah, so you'll get the class name, you will get the accessibility identifier, and you will get the actual frame of the particular view.
So the frame is actually accessibility
frame. No, it's just the normal frame.
Yes. Do you guys do like enterprise stuff as well?
We are currently working on it. Our SaaS is in staging right now. We should be able to launch it in like 3-4 weeks or so. A beta version of it will be available in like 2-3 weeks. Yeah.
Any other question, guys? I had a couple of questions, but most of them have been already asked by especially I was asking about the mic one, and I was like, how complicated can it be if you have this working on iOS to make this working on macOS? But I think you answered the question.
Yeah. I think Apple's ecosystem and the whole developer experience is good enough that most things now just work by default everywhere. And given that we are just not relying on UI so much, so most of it works. The only thing is that there's a few things that are still finicky, right? So the way we generate layout snapshots is by getting the current frame information. Now the pixel density of newer MacBooks is so high that if we just pass along that frame size to a SVG generator, it just dies. So there's these few weird things that end up happening when you're distributing something on a completely different platform. So we just need to make sure we iron out those bugs. Currently, there isn't a huge amount of requirement from the macOS side of things. That's why we are focusing mainly on the iPhones and the iPads. Once we have those two sorted out, we'll focus a bit more on macOS as well. But that is definitely in the pipeline, that we want to support the whole Apple ecosystem, not just the iPhones and the iPads.
And so you started with iOS, Android, and then Flutter and React Native. Is there anything like, is it why React Native is the last one? Because it's the hardest one? Like, is there any?
No, we didn't have any React Native developers.
Yeah.
So
the thing is hardcore native engineers. Flutter and native, right?
Yeah. So the thing is that our Flutter SDK and React Native packages are just a wrapper on top of the existing iOS and Android framework. So we didn't want to create a whole new package for Flutter and React Native. So we made sure that we sort of created these basic frameworks first on iOS and Android, and then adding React Native and Flutter support is just a matter of creating a wrapper on top of the existing thing.
I have one.
Yeah.
Yeah.
Yeah, I have one, but I forgot. So no, I forgot. So just I forgot my question. So go ahead until I find it again.
You guys also support integrations like with PagerDuty. So if you suddenly get a lot of crashes, it integrates with PagerDuty. So like an engineer who's on call will get an alert.
So we have created a basic alerting system for now. So we do send, we have email integration and Slack integration, but we don't have a consolidated system put in together. As of now, we are currently working on it. It should be up and running as soon as the SaaS has launched up.
Because I think that's one that's very important for us. Having PagerDuty integration would be critical.
I'll take a look into that.
I like the snapshot idea, because we tried the Sentry one, and like I said, it works. There is definitely an overhead. It's not noticeable, at least not to the user. The quality of the video is that's for sure. It's more like a 240p maybe. Compressed like hell. The frame rate is like 5 maybe.
But they just generate like screenshots and video out of it.
Yeah. So they just generate a screenshot in an interval of 2 or 3 seconds, and then they just generate a video out of it. But again, it's to us, we did explore that particular approach. Now, again, the problem is that Apple allows a transition time of 500 milliseconds from one screen to the other, and generally says that if your app sort of responds within 500 milliseconds, the interaction feels very seamless, right? So the problem is that again, if you take a screenshot, the whole process of capturing a screenshot itself ends up taking 70-75 milliseconds. Then you have to redact a bunch of information there, because you never really know where the screenshot is being taken. That adds up a bit of processing there. Then again, we are internally using core data to manage and save all of the data locally. Because layout snapshots are about just 4 or 5 KBs, it just gets saved into the SQLite directly. Now, because screenshots are way more heavier, you need to save it to the local file system. Then you get a reference out of it, then you save that into the local database. Once you add up all of these processes, there's just no way you can keep on executing that with the just time of 100 milliseconds. It just ends up taking so much time that the user behavior, like the user interaction, just becomes very janky and slow. So, but with layout snapshots, even if, let's say, the worst of them take not more than 20 milliseconds, it's still so seamless and falls well below like the 500 millisecond interaction time set by Apple, that you just do not even feel that there's something that's being collected in the background.
Yeah, I was thinking that what you're doing, like the work you're doing building this SDK, especially in the analytic crash reporting area,
Yeah.
you might have seen things that for most of us, like app developers, like just building a service, we might never see or never have to experience. Is there like what's the top one thing that like working on this SDK, especially with low level API or like maybe some intricacy of the UI kit framework or whatever, something you've seen that you can
So
you can
I'm not sure whether it falls in under the pure iOS category or not, but what I've realized working on this is that firstly I had to actually figure out how actually iOS runs a particular application, and even just starting from that base point, what I essentially one thing that was surprising to me and pretty shocking, but it now seems so obvious, is that the amount of abstraction that we have in the modern software engineering world is incredible. Like at the binary level, everything is of course ones and zeros, but then you've got the kernel, you've got the whole system, you've got the whole process, then there's a bunch of threads. The right now when you're writing code, you're not really thinking about any of that, and I think that is just the biggest differentiator here. When you're writing a monitoring SDK, the biggest challenge is sort of every single microsecond counts, because again, as I mentioned, we're collecting everything from lifecycle to CPU usage to memory usage. Every single piece of code you add is not just the core piece of code that you add. It's also amount of time that you are adding to every single pre-existing workload. And I think the amount of abstraction that we have sort of working with these low-level APIs, we just do not see on the top level what's actually going on. It's just, okay, click this button, it will work. Nobody really cares about how internally that particular touch is being created, how that touch is then passed along to all of these controllers, and then essentially at the end of it all, firstly, how a touch is created even, because at the end of the day, it's just a capacitive touch screen, right? So you're just getting the point where a particular gesture has happened. Then how do you sort of convert that point itself into a particular touch event? Because iOS has many, you've got multi-finger touch, drag gestures, so on and so forth. So just interacting with the UI touch API as a developer is just so easy, right? But how do you even get from the coordinate system to the whole, UI touch object? It within itself is very fascinating. So to me, that was the biggest sort of surprising thing about how many times we just end up writing code, not really knowing how complex of a task it is performing internally. And to me, that was really fascinating.
Nice. Maybe last one for me is, I don't know if you touched on this, but in the piece of code you were showing in the middle where you open the file and then you write on the metadata and so on. I was just curious.
What if disk is full? You crash the app?
And to this extent, I was like, when the crash happened, you have crashed, and then you have to stop, and is there, how many seconds when the crash comes can you still, so you record some information when someone clicks and so on, but when the crash happens and the app just shut down, like between this shutdown, like it just reminded me of, is it when you touch about push notification, where when you put in the program, you have a couple of milliseconds to do
when do you save your code data?
Where can you actually handle things? Like how many times you have when the crash happens to actually collect a bunch of stuff? Maybe I was curious about that.
Yeah. So what ends up happening is that as soon as the signal is triggered, right? Signal handler is the last piece of code your app is going to run. Once that piece of code is run, everything else is done after that. So now I know a lot of people might think that you could technically, what you could do is you could just spawn off a new process as soon as within the signal handler itself. Now you could do that, but you could end up resulting in a deadlock or some sort of a memory issue where it will even mess up the current state of the app even more. So crashes usually happens, when explicitly the OS wants to shut it down, and it's not just down to security risk. More often than not, it's down to because it wants to save the application, because so that it does not lead to data corruption or some sort of a corruption in the operating system itself or within the data of your app. So what it does is essentially, as soon as the signal is triggered, the app process itself has gone into the crashed state. Now, from the crashed state, the last thing it will do is essentially stop the the execution pointer just stops, and then it just moves ahead to the signal handler. And as soon as your signal handler is done, your app just ends there. So whatever point the crash was triggered, that is how the backtrace is also collected, right? So there's a particular instruction at the end of the day on the CPU level that triggers a crash. As soon as that instruction level is reached and the crash is triggered, your process is killed at that time. And then the signal handler code starts running. So signal handler is just a catch that you get that, you can, your app is crashed now, just run, save some data, or do whatever low level things that you want to. So at that moment itself, what the PL crash reporter or case crash they will do is they'll go through the backtrace at that particular point itself, because the immediate point where they handle the particular signal, the app process has crashed at then and there itself. So signal handler is the last thing that your app runs.
Signal handler is actually a C function, and it's a special OS API which you tell OS that this is my signal handler. Whenever you receive a signal, please invoke this C function. So signal handler always works outside your process. So even if the process is crashed, signal handler can still run. Maybe in traditional C programs, it does an object dump, obj dump. So as you can, there is a .d debug file is generated whenever some C programs or other, like old Unix systems, they used to generate those things. So you pass on this dump to the obj dump command and symbolic it kind of thing. So that's how this system works. This works outside the process, as Adwin is saying, right? And that's why you have a fixed stack pointer, program counter. You can take the stack trace, thread position, everything, and print it.
Is there any limit of time you can do stuff in this cache? Is there a limit of memory you can?
What if you just start mining Bitcoin?
Yeah, I mean, like I'm just curious, like, is there any limitation on what you can do? It's like just restart. Yeah.
That's the thing, right? What you mentioned is because the process is kind of a suspended state, or it's basically done. And you cannot move the program counter for that particular process. You can spawn a new process, as you said.
Okay.
Yeah.
So you're free to do exactly what you want.
What you want. Yeah.
Yeah. iOS does not allow you to do it because iOS is a sandboxed environment. But again, if you do it on Linux or some other place, you can go ahead and as soon as your app crashes, you can respawn your whole process again. You can do that via signal handler.
That is how
that process is crashed now.
Yeah. That is how it is done. A lot of times you have these exam apps. When the app, when you are running an exam, you run in a control mode or something, right? So even if you try to kill the app, it automatically restarts.
Yeah, but I thought there was some kind of limitation on the memory you can use in this case, or maybe
you cannot use memory for that system, that process.
Okay. But so it means it's not in this process that you actually send the data by the network to your I mean,
it's a new process. Yeah, you can create a new process, send the data on network.
So that would work. Okay.
So in this signal handler, I could start a loop. That doesn't stop. Would that
I mean,
crash the
OS
system?
will kill
Would
it
that
eventually.
crash the
OS will
system?
kill it eventually.
Yeah, that's
So
the
it would
question.
kill
When?
How when?
So because the Mark kernel or Unix kernels, right, they have this priority inversion system, right, or deadlock identification. Whenever it identifies that a child process is functioning more, maybe then if it has its own signal handler, I don't know what it's called.
You have a signal handler for a signal handler?
No. No, you can't. You can just have one single signal handler
Yeah.
for the whole process, which just gets called whenever the app crashes.
So why? I'm just curious because, sometimes I play PUBG, and PUBG is very funny because when they have a download, when they have an update, they update, and then they make the app crash voluntarily.
I thought that's not allowed, right?
So
I've
why
seen
not
that somewhere
they
too.
make it restart by himself? It's like
So
No,
in
very
iOS, you can't really respawn the process because in iOS, your applications work in a sandboxed environment, right? So in iOS, you can't really do that. Whereas in your bigger Mac OS or Linux or Windows, you can just keep on respawning new processes as soon as you end up getting a crash.
cool. I mean, this is something I never pay attention to. So it's like, very nice. Any last questions, guys? No? All right. Thank you so much.
Oh,
man.
thanks,
Thank you so
Adwin.
much.
Thank you very much, guys. It's been a blast. See you guys soon. Bye-bye.